All right, and I'll pull the screen up here, folks, the whiteboard. And as I said, today is going to be a simple lesson about continuity. All right, very simple concept. You'll easily be able to understand it. 1.8 continuity. So continuity for a function, continuity is a concept that can be defined both locally and globally. That is, a function would be continuous at one point, but also you would discuss about the function being continuous everywhere. So I'm going to start with a global concept if you want, and we're going to say here that a function is continuous everywhere on its domain if we can draw its graph without lifting the pen from the piece of paper where we're drawing. Let me move this thing here. From the drawing surface. So examples of continuous functions. So if you want to talk a continuous function, for example, this would be one of them. So there we go. You can draw its graph without lifting the pen from the drawing surface. This is an example. A simpler example in a way would be this example when you draw a straight line, things like that. So these are all graphs of continuous functions. All right, so now the notion of continuity is also, this is the concept of global continuity. So basically, folks, what you see here, there is no breaks in this graph. However, we can use the notion of continuity also locally. And locally, well, that's a different story. The function would be continuous. So locally, we say that a function f, my pen isn't working very well, a function f is continuous at, this would be a function f of x, let's say, at it's continuous at x equals a if the limit as x approaches a of f of x is equal to f of a. So what am I saying here, folks? What I'm saying is that so let's kind of take a little bit of break from the definition here, and let's review the concept of limit, and let's see what happened there. So we said that with the concept of limit, we could have a situation like this. We could have a graph that goes all the way up to here. Let's say this is a point, I don't know, let's say a point 4 on the x-axis. Goes all the way up to here. There's a break here, so we don't know. Maybe you don't even have a value there. And then continues something like this. So this is the graph of some function, some random function. I'm going to call this function f of x. So what you notice here, and we said when we discussed limits, to talk about limits, all that matters is that when we approach the corresponding point from the left and from the right, remember the point on the graph will be sliding towards the same position. So there we go. So these two slide toward the same position. And this point here is at height, I don't know, at height, let's say this is a height of 3. Then we say that the limit is 3. In other words, what's important here, and we get so I gave this kind of colloquial example if you want. So to have a limit, it matters. So as we said in our class, it matters value in the neighborhood, not necessarily what you have at your own house. So if you measure, if you are a real estate agent and you look at the neighborhood and for a house in the neighborhood, maybe the value of a house is not available for whatever reason, but you somehow can figure out that every other house in the neighborhood is worth $100,000 or around $100,000. And you can conclude, and would be a fair conclusion to say that even there where you couldn't measure your value, you would also have a value of $100,000 or close to that. So that would be the concept of limit. It matters what happens in the neighborhood, but not at the house, at your house. So whether your house is $1 million house or a $50 house, it's unimportant, because the conclusion that the realtor drew is based on the neighborhood, values, and then the realtor will conclude that the limit is that, and that might be wrong, So the real value may not be 100,000, as I said, but the limit of the values of the houses in the neighborhood is 100,000. Continuity is the concept that pushes the concept of limit a step further. So not only is it important what happens in the neighborhood, it's important that the houses in the neighborhood, float at about 100,000 in value. It's also important that your own house, when it's evaluated, is also at that value at 100,000. So continuity is the concept where it's important that the value of your house matches what's inferred from the neighborhood houses. So if the neighborhood houses cost all about 100,000, then your value, your house's value, if it's a continuous function, has got to be 100,000. So that's the concept of continuity. So whatever happens at my house should match what's happening in the neighborhood. So then we say that it's a continuous function. So that's what happens here, and that's why we say we formulate the concept of continuity also like this. So we say that the limit as x approaches, and this is the same as the one here, but the one here it's a little hidden, because remember when we define functions, limits and such, we do limits from the left, limits from the right. So the limit as x approaches a from the left of f of x has got to be equal to f of a, and that has got to be equal to the limit as x approaches a from the right. So only then is the limit equal to f of a. So because if these two limits, the left and the right side limits, are equal to f of a, then the limit will be equal to f of a. So that's the condition of continuity. In practice, we check for these to be equal values. All right, folks. So this being said, how do you recognize continuity on a graph? So that's the next step, and then I'll show you how to recognize continuity algebraically. So on a graph, so I gave you the abstract definition there. On a graph, continuity means no jumps. All right, so what kind of jumps can we have on a graph? Well, we can have the following situation. So you can come, say, from the left and end up at a point here, and then maybe there is a value here, and you can continue like that. This is called a jump. So there's a discrepancy in the approaches from the left and from the right. So that is discontinuous. It's a function that's not continuous or discontinuous. another situation. So in this case, not only is it discontinuous, but it doesn't even have a limit because the limits from both sides are different. But here's an example. So we can give a similar example when we go here and then we go this way. So this graph looks like it's a continuous graph, but I'm going to define the value of that function to be somewhere here. So at this point, let's say this is the point 3, this is 3 comma 1, and this is 3 comma 2. So I define my function f to be everything, outside 3 here, everything that's on this graph, and over here, this point. So basically, folks, what I'm looking to define here is a function that still has a jump. This counts as a jump. So if I want to move from left to right on the graph, what I have to do, I have to go all the way very close to this point, make a jump at this point here, and then come back and continue on the right side of the graph. So this is another example of a discontinuous. Now, in the previous example, the side limits are not equal. In this example, the side limits are equal. And not so the limit here, the limit exists. So the limit as x approaches 3 from the left of f of x, in this case, let's say is equal to the limit as x approaches 3 from the right of f of x, and is equal to 1, this value. So the limit exists, but the two are not equal, but they're not equal to f of 3, which is 2. So that's the reason why this function is discontinuous. And folks, if you understood this much, this is as simple as the concept is. So these are examples of discontinuous functions. Now, in practice, what's going to happen if you solve a problem? Most of the so these discontinuous functions are tricky, and we don't like to deal with them most of the times. Like when you solve a math problem, people expect some sort of continuity, so people don't like discontinuities. For example, in the stock market, let's say one day the stocks go up and suddenly the next day when they start, I don't know, 100 points lower. That's a bad behavior, bad type of behavior. So stocks tend to be discontinuous as a function of the stock value. So what would you like to have here to make sure that there is some sort of continuity? Well, you would like to work with continuous functions, or even better, you would like to model discontinuous situations by some sort of continuous function. In other words, a function that's approximately equal to the discontinuous one, but doesn't have breaks in the graph, doesn't have branches. So most of the time and most of the calculus that we will learn here, folks, is dealing with continuous functions. So everything here is essentially going to be a continuous function from this point on. Let me give you examples of such things. So examples of continuous functions. So fortunately, most of the functions that you know from pre-calculus or college algebra are continuous functions. And that helps us a lot to apply the techniques of calculus. Not only are they continuous, but they are also smooth, so they don't have corners in the graph. So examples are the polynomials. These are very much continuous. So every single polynomial is continuous. What else is there that's continuous? So polynomials meaning, sums of powers of x, something like, let me just give you an example here, 2x squared minus 3x plus 1, if you think of this as a function of x. So, so there we go. This is an example of a continuous function. All right. So this is what we're working with, and then we do basic trigonometric functions, sine x, cosine x, oh, they're continuous. But the problem with trigonometric functions is that there would be places where they are discontinuous. So these are fine. Sine and cosine are fine everywhere. However, tangent x is discontinuous, so it's discontinuous at points like negative pi over 2, pi over 2, negative 3 pi over 2, 3 pi over 2, so plus minus pi over 2 plus a multiple of pi. So let's see why that is the case, because if we draw the tangent function, and I'm going to share a screen with you folks in a second. Let's draw together the tangent function in Desmos, of course. We're going to go to Desmos here. Okay, you cannot see it. 1 second, folks. Find the share screen. There we go. So, so the share screen is here. Let's graph, and let's do y equals tangent of x. What is x here? There we go. So so look at this. One thing that I don't like, I don't get the radians there. So let's make sure that we put radians on the x-axis. So we're just that's a simple trick here. Just make a step of pi, for example, and as you can see, you know what? Let's do pi over 2. As you can see, there we go. So that's much better, because this tells us exactly here that this function breaks down at pi over 2, for example. So if you look on the graph, it's continuous. Like if you consider the basic interval negative pi over 2, continuous there, but then it gets here, so you have to jump if you want to move on the graph from pi over 2, from the left of pi over 2 to the right of pi over 2. You have to jump from all the way up here down to the other side to continue drawing the function. So this function has a bunch of points of discontinuity, and it's a bit trickier, so we have to pay attention when we work with this function. All right, similar functions that are discontinuous at some points are this one, secant x, the exact same situation. So it's discontinuous at pi over 2 and negative pi over 2, cosecant, cotangent, and so on. So, so these are functions that are not continuous everywhere. They have intervals of discontinuity. Let me share with you the other board, and let's say here, but tangent is continuous elsewhere. Similar situation with secant x, which, by the way, everybody remember that secant is 1 over cosine, right, folks? It's also discontinuous at plus minus, pi over 2, 3 pi over 2, da da da. So, so it is discontinuous there, but continuous elsewhere. All right, so this is the situation with trigonometric functions. And then we have the exponentials, which really we do not study in this class. So that's the subject of calculus 2 for those who will take calculus 2, e to the x, log x. These are continuous on their respective domain, on their domains. Likewise, square root of x is continuous. By the way, square root of x is defined on the interval 0 to infinity, so be careful there because it's not defined everywhere. All right, so these are examples of functions that are continuous, and you can see by looking at this table that I listed here, this list that I made here, you can see that essentially every single function you can think of as of having some sort of significance or meaning to you will be a continuous function, and that is very good because really we want to do calculus. We want to learn more about these kind of functions, and that's what we're gonna do. Now there's another selection of functions that it's not continuous. Well, it's continuous almost everywhere, but not all over the place. And those functions are the rational functions. We are going to deal with these as well. So with the rational functions, again, kind of like we did with tangents. So everything is okay almost everywhere except for one or for a few points. So when you have rational functions, I could list them. These are continuous on, but they're continuous on intervals, I'll say, of definition. In other words, so they're continuous on their domain, but remember that domains for rational functions, so if you have, for example, something like f of x equal to 1 over x, remember that you need to exclude 0, so the domain of this function will really be, this function is defined, and it's a couple of continuous branches, but defined, if you define it on negative infinity is 0, exclude 0, together with 0, infinity. So that definition that I gave you at the beginning is a bit misleading here, because you may say, oh, but look, I am trying to draw the graph of this function, but I have to sort of skip here from one branch to the other. Well, that's not really the case, because this graph is really only defined above, so it automatically skips 0 because of the domain. 0 is taken out of a domain. So the continuity, the concept of continuity is in the end best described if you describe it locally at every point. When you approach the point, any point here, as you can see, when you approach the point from the left and from the right, what happens here? So you're gonna get something here that is continuous, in the sense that a point on the graph slides towards this one, and the value is the one that's given here. So this is the situation of continuous functions, and so these the functions like this, which are rational functions, in other words, quotients of polynomials, qualify to be called continuous. Just be careful to remove points where they are not well defined. All right, so this is the concept. Now I am going to be left with one thing here, one calculation of limit that is very important, and is going to turn out to be useful in the following chapter. So there's a bunch of other things here. Compositions of continuous function is continuous. The sum of continuous functions is continuous and things like that. But the reality is that other than some sort of theoretical meaning, those do not have much of a practical consequence for us. So again, folks, from this point on, from next time, all the functions that we work here with are more or less continuous, or if they're not continuous, that's going to be a really exceptional situation. So there is, I said there is one example that I want to do here, and pretty much I can close with that. Again, this is not a big lesson here, and I wouldn't want to spend a ton of time on this lesson. So a calculation of the limit as x approaches 0 of sine x over x. Now, we did this calculation before. Folks. And this limit turns out to be 1. But the thing is, and this is a key place in calculus that shows the importance of using radians instead of degrees. So we're looking at calculating this limit by using some sort of intuitive method. So let me explain you what the intuitive method is. Now, this is a good review of pre-calculus or college algebra in trig, if you took that recently and stuff like that. So this is the, you know what, I can do this more precisely. So there is a thing here that would draw these things for me. So folks, oops, sorry about that, clicked on the wrong button. So there is a thing here that gives me straight lines. So let me do straight lines. So this one, all right, and this one here. And there is also a thing here that gives me circles. I think this is a circle, would be a circle. Oops, not that. Oh no, oh, okay. No, I don't want that. So, all right. Okay, I deleted too much. Sorry about that, folks. It's a bit cumbersome here. To draw on this pad again, they don't have the geometry function, is not perfect, but I got the idea here. All right, so I'm gonna do a circle. Let's try again. A circle. Oh no. Okay, now that. Okay, let me delete that. I'm gonna start the circle from here then. All right, so all right, so let's do the circle from here. How do I not get that? Sorry about that, folks. Ooh. All right. There. Oh, okay. So I'm almost there. All right. Let's do again. Oops. Come on. All right. So I'm gonna do the circle and then I'll draw the other line. Okay. There we go. Okay, so I'll do that. Let's say that's the unit circle. And now I'm finally going to draw the other line. So this way I know that there we go. So that's a trick that I didn't know before. All right, folks. So at this point in time, I apologize. This is kind of I apologize. This is so the technology is not perfect here. So let's say we have an angle theta, right? And then that's an angle theta here, and theta goes to 0. So by the way, in this example, I should have said limit as theta goes to 0, just to represent that we're talking an angle sine theta over theta. And when theta goes to 0, sine theta is this line segment. So is the y coordinate of this point, of the end point here, the terminal point here on the circle. So this is sine theta. So this guy here is sine theta. And theta itself, now this is the key part. So when we measure in radians, theta really means the arc length along the circle over here between this point, which is 1 comma 0, and this is the unit circle, by the way, and this point here. So so this is theta. And now when you do the quotient of these two, you can see that as you're going closer and closer, as this thing gets closer and closer to 0, the angle theta, these two, the arc length and this segment, are approximately equal. So theta is almost equal to sine theta if we measure theta along the circle. Along the circle. So that means radians. If you don't measure along the circle, you measure in degrees, then this angle, this theta here will not be the measure. Remember that that will be pi times. So so the arc length is pi times the length in degrees. So so what you get here, so these two numbers will not be approximately equal if theta is measured in degrees. Now, because these are approximately equal, the quotient sine theta divided by theta is approximately equal to 1. And that's what we verified with Desmos. So, so this limit is 1, but that's assuming that our angle theta is measured in radians. This is the important thing. Now, if theta were measured again in degrees, then there is a formula that, so the formula, degrees to radians, and that formula is, you know, 180 degrees is pi radians. So if you want 1 degree, that's going to be pi over 180 radians. So, the formula here, the formula that you would get here, if you were to substitute theta in degrees, you would have to say that in radians, you know, there is this extra factor of pi over 180 that would influence the result. So that's why in calculus, it's essential that you always work with your angles in radians, not in degrees. I mean, you can think of it in degrees if you want, but remember that always, if you want to get a clean version of calculus, you can certainly work with degrees. But if you want to get a clean version of calculus, what you want to work with radians, and that's because of this limit here. And this limit turns out to be very important. We'll see it again soon in the next chapter. Sine x over x when x approaches 0 is going to be equal to 1. We can do this exercise. I think we did this exercise earlier, but we can redo this exercise just to convince yourselves, folks, that that this is the case. So when we work with radians, we do get that limit to be 0, to be 1. So I'm going to pull here. I'm going to pull another. Okay, so I'm going to do this thing here. Let's clean up the stuff here. So let's say f of x equal f of, you know what? Let's say f of yeah, let's say x. All right, equals sine. I'm sorry, sine x over. Oops, not that. Okay, so let's do sine x over x. There we go. So we got sine x over x here, and we can do a table. And in the table, I'm going to put t, and like we usually do, and f of t here. So all right, and we can do values of t, but now remember, I want those values to, I want to make sure that my thing is working with radians, so I want to put values like these, pi for example, pi, just type it pi and you get 0 there. Then you do pi over 2, pi over 2, and that's going to give you a limit, a value of 0.63. Then you do pi over 3, pi over 3, and that's going to give us a value of 0.82. And then you can do pi over, I don't know, pi over 12, let's say, and that's going to give us a value really close to 1 here, folks. You can see the points plotted on the graph. Look at that, how nicely they go towards my point here, which is at the top, and that's going to be close to 1. And you can give values in this table very, very close to that. So to 0, something like pi over, let's say, 100. And it's really close to 1. Now look at that. So 0.9998 something. So that's really close to 1. All right. So so this limit is 1, but again, it's important here that we do calculate the angles so we do calculate this with radians. So if you want to switch to degrees, you will see, and you can calculate this same limit. So let me see if I can figure it out here. I forgot to think of that in degrees. Let's say we want to do the x-axis in not in radians, but oops, let's see if it gives me the option of doing degrees instead of radians. Oh, there we go. So let's say we do degrees here. You will see that it's the calculation is not going to be the one that you want. So, so I'm going to do degrees here. So again, I'm going to switch from radians to degrees, and you will see that this limit is not going to be 1 anymore. So, so look here, folks. Let's see. Let's do the table again. Again, a t and f of t here. So f of t. What happened with my t from here? That disappeared. I'm going to put that back. So I'm going to put angles. I'm going to put angles that are very close to 0, right? So 90 degree will be an angle, and then 45 is another angle, and then 1 is very close to 0, right? Is another angle, and then 0.01, and it looks like with the angles as you're getting closer and closer to 0 with, now remember this is in degrees this time around. As you're getting very close to 0, what happens here, this number is getting very close to something else, 0.001, let's say. It's getting very close to 0.01745, etc. Now, what is that thing? Remember that we said that extra factor when you convert from degrees to radians. So for radians, things work so nicely. You know, the limit was 1. It didn't have anything to do. For if you work with degrees, folks, and this is again what I want to emphasize, that's why it's important to work with radians in calculus. If you work with so remember that formula that changes from degrees to radians. So if you calculate pi over, pi over 180, it's going to give you exactly that. So it's this is the limit. This is the conversion formula for degrees to radians. So this is why this limit is, if you measure x in degrees, is not going to be 1, but rather this number, which is pi over 180. So, so that would be another version of calculus. Again, you can carry out everything that we do here in calculus if you want to work with degrees, but this would be another version of calculus that would not be particularly useful for us, because it would be very cumbersome to do the calculations when you have pi over 180 and things like that. So as a coefficient, so it's not very pleasant. So this is what I wanted to tell you for today. There's a few other examples here in the book, and you can look at them and you can see, well, let's see, is this continuous or not, this particular function, and so on. But again, I'm not going to insist on those. So what I want you to understand though is that again, the idea of continuity. So now we're done with this thing here. So let me stop sharing this screen. So folks, the idea of continuity is the idea of having no matter how I go, I still run into that example. So is the idea that I did here at the beginning of the hour. So so these two would have to click, the two branches at one point would have to click at the same point, kind of like in this case, and the value would have to be there too in order to have a continuous function. And there's going to be a bunch of graphs in the book, especially problems I see problem 3 and problem 4. I don't know if you can see them on my camera. So 1 second, let me just stop sharing this thing, and let's see what I don't even see what yeah, it doesn't show anymore. But whatever. So the example is this one here, example 1.8. So if you see in the camera, and this is a graph example. In section 1.8 exercises. So this is an example with a graph, and the points of continuity and discontinuity are represented there. So I'm not going to copy because I don't have much time here. Are represented there. It's where there are jumps in the graphs. So I invite you to do those problems. And there is not much else that I would ask from here. So there is a bunch of other questions that you could ask. So I will put a practice problem, bro, from this section, something like number 45 or 46, where you would have to kind of figure out a constant to make a function continuous. All right, so I'm going to stop recording here, folks.